Hey guys, welcome to Magnetism Part 5. At the end of the last video, I gave you a challenge. How would you set up a magnetic and electric field in order to keep a positively charged particle moving in a straight line at a constant velocity? In this video, we're going to seek to answer this question, and we're going to compare and contrast the electric and magnetic field. So let's get into it. Now, in order to answer this question, I oftentimes find it helpful to either rephrase the question or to ask sub-questions in order to find the answer to the ultimate question. So another way I could ask this question is, how can I prevent the helixing from happening? That then leads me to another question. How does the helix pattern occur? Now we know the helical pattern, or at least the circular motion portion of the helical pattern, occurs because the magnetic force always acts perpendicular to the velocity of the moving charge. In order to get more information on this, please go back and watch videos 3 and 4. So now that we've identified how the helical or the circular pattern happens, and we know that we want to prevent it, the question becomes, how do we prevent that from happening? So in other words, I can rephrase the question, how do I prevent the magnetic force from being the net force, or being the only force and therefore a centripetal force? This question could be posed in much simpler terms. If I took a box and I said there's only one force acting on it, how do I prevent it from accelerating? Well, most of us would say very simply, just apply an equal force in the opposite direction, and that will prevent there from being a net force. So that's what we're going to do here. We're going to come up with a force that can point in the opposite direction to the magnetic force, thereby making a net force of 0. And when there's a net force of 0, an object should be moving in a straight line. So in order to continue answering the question, I'm going to arbitrarily choose, say, the magnetic force to be pointing straight down towards the bottom of the screen. So with the magnetic force pointing down, I realize very simply that I need an electrostatic force to be pointing up. In other words, I need to have a force diagram that looks like this, where both forces will end up canceling one another out and there being a net force of 0. So the question now becomes, how do I orient a magnetic and electric field in such a way as to create an orientation of the forces, like in my force diagram above? To answer this question, we're going to have to work backwards first using the right-hand rule. Now, I arbitrarily said when I did the force diagram previously that the magnetic force is pointing down. So using my right-hand rule, how can I make the magnetic force point down? Well, I have to have my thumb aligned with that magnetic force. Now, because we're using a positively charged particle, that leaves my index finger pointing to the left and my fingers pointing into the screen. So that means that I need to have a magnetic field where the field lines are directed into the screen, which I'll represent with X's. And I know that I'll have to launch the particle with an initial velocity to the left. This is one possible way that I can have the magnetic force pointing down. So now I'm going to ask you to pause the video and try to come up with a way that you can still have the magnetic force pointing down, but with a different orientation where the particle's velocity is no longer to the left. Well, if I direct my thumb down, but this time have my fingers pointing out of the screen, represented here by dots, I can see that my index finger will be pointing to the right. So I could really have the particle either moving to the left or to the right, but in order to maintain a downward direction of the magnetic force, I have to orient the magnetic field either out of the screen or into the screen, and that would cause the direction of the velocity to flip. So because it's easier to hold my hand that way, I'm going to say let's have the magnetic field pointing into the screen. Now the question becomes, what direction should the electric field be pointing in order to establish a net force of 0 between the electrostatic and the magnetic forces? So once again, I'll say pause the video and try to answer that yourself. So to answer this question, We're going to go back to our force diagram with the magnetic force pointing down, and now knowing that we need the electrostatic force to point up. So we'll have to ask ourselves the question, how is the electrostatic force related to the electric field, so that we can know which way to orient that electric field? So recalling from electrostatics, I know that the electrostatic force either acts 0 degrees to the electric field lines or 180 degrees to the electric field lines, depending on if I have a positive or negative charge. So knowing that I have a positive charge in this case, and I want the electric force to point up, I will also need the electric field lines to point up in the same direction. The question then becomes, how do I construct a scenario or an apparatus so that I can have the electrostatic field pointing up and the magnetic field pointing into the screen? Pause the video and try to determine how you could create a setup that would result in that orientation of electric and magnetic fields. Well, for the magnetic field, I know that if I'm directing the magnetic field into the plane of the page, I would need a north pole of a magnet on, say, the outside of the screen, and I would need a south pole of the magnet on the inside of the screen. In other words, I need to have the magnetic field lines pointing from north to south. Now, for the electric field, I know that I can construct a uniform electric field by using capacitor plates. So I could place one plate down here at the bottom and one plate up here at the top, and the orientation or the polarity of the plates would have to be a positive plate on the bottom, because I want the field lines to point away, and a negative plate on the top. Now keep in mind, this is just a general setup. There are many different versions of this setup that can prevent the charged particles from moving in a helix or circular pattern. Let's see if I can now mathematically describe this constant velocity of the charged particle. So if I go back to my force diagram, I know that my electrostatic force and my magnetic force have to be equal to one another, or sum to 0. If I substitute the equations for each in, Q V cross B for the magnetic force, and Q times E for the electrostatic force, I can see that the charge of the particle will cancel. If I then divide on this side, I am left with E over B as a ratio for the velocity. So any combination of E, the electric field strength, to the magnetic field strength can determine a constant velocity needed to keep the particle moving in a straight line at the same speed. So you can see that using the electric and the magnetic fields together can be quite complex. It's therefore very important to know the components of the electric and magnetic fields very well. One way to do this and to keep them straight in your mind is to compare and contrast them. So let's do that. One of the first and major differences is that the magnetic field can only act on moving charged particles, whereas the electric field can act on stationary or moving charged particles. We will explore why this happens in a lot more detail in the next section of this magnetism video series. Another important difference is that the electric field can exist from a monopole source, whereas the magnetic field has to exist from a dipole source. This leads to another major difference. Electric field lines have an origination and a termination point, whereas magnetic field lines are continuous and do not originate or terminate. Lastly, the electrostatic force always acts parallel to the electric field lines, either at 0 degrees or 180 degrees, depending on if we are looking at a positive or negatively charged particle within the field. The magnetic force, however, always acts perpendicular to the magnetic field lines and depends upon the direction that the charged particle is traveling relative to the field. Finally, I'm going to share with you a silly but effective way that I've used in the past to help remember which is which. Being an original Jurassic Park fan myself, I always remembered that the T-Rex could only see you if you were moving because of its depth perception, whereas the Velociraptor could see you whether you were moving or not. So I often tend to think of the magnetic field or magnetic force as a T-Rex. It only detects moving charges, not static charges, whereas the electric field is more of a velociraptor. It can detect moving or stationary electric charges. In the next video, we're going to take a look at how the foundation of the electric motor is formed when a current-carrying loop of wire interacts with a magnetic field. Hope to see you back for the next video.